Let's explore the fundamental concepts of containers and virtual machines. First, let's understand containers. A container is a lightweight, standalone package that includes everything needed to run a specific piece of software. Containers are designed to be lightweight and portable. They include the application, necessary libraries, and dependencies, all bundled together. In contrast, a virtual machine is a complete copy of a computer system, including its own operating system and virtual hardware. Virtual machines provide complete system isolation by simulating an entire computer, including hardware resources and a separate operating system. Both containers and virtual machines achieve application isolation, but in different ways. Each application runs in its own isolated environment, preventing conflicts and ensuring security. Let's compare how containers and virtual machines approach isolation differently. These fundamental differences in approach lead to unique advantages and use cases for each technology. Let's examine how containers are structured. They share the host operating system's kernel, making them extremely lightweight. Containers run as isolated processes, sharing the same kernel but maintaining separation through namespace isolation. In contrast, virtual machines use a hypervisor to create completely isolated instances, each with its own operating system. Each virtual machine contains a complete copy of an operating system, including its own kernel, libraries, and system resources. The architectural differences lead to significant variations in resource usage. Containers typically require only megabytes of space and minimal memory. Container startup times are typically just a few seconds, while virtual machines can take several minutes to boot. This graph shows how resource utilization scales with workload. Containers maintain lower overhead even as demands increase. The memory footprint difference is substantial. A typical container might use tens of megabytes, while a VM requires gigabytes of memory. Let's examine the security implications of virtual machines and containers, starting with VMs. Virtual machines provide strong isolation through complete hardware virtualization. Each VM runs its own operating system and has dedicated resources. VMs offer several key security features. They provide complete hardware isolation, separate operating system instances, independent memory spaces, and dedicated resources. Now, let's look at container security. Containers use a different approach, sharing the host operating system kernel. Containers implement security through process-level isolation, using features like namespaces and control groups to separate processes and resources. Let's examine the potential vulnerabilities of both approaches. Virtual machines provide multiple layers of security boundaries through hardware virtualization and separate operating systems. Containers have fewer security boundaries, but offer more efficient resource usage and faster deployment. Let's compare key security aspects of both technologies side by side. Understanding these security implications is crucial for choosing the right technology for your specific needs. Let's examine the specific scenarios where containers and virtual machines excel. Containers are ideal for microservices architecture, continuous integration pipelines, and rapid development environments. Virtual machines shine when running different operating systems, legacy applications, or when complete system isolation is needed. Let's look at some real-world examples. For containers, we commonly see e-commerce platforms using microservices, development environments, and API gateways. Virtual machines are often used for running Windows applications on Linux hosts, dedicated database servers, and legacy enterprise systems. In a microservices architecture, containers allow us to break down applications into small, independent services. Traditional monolithic applications often run better on virtual machines, where each component gets dedicated resources. Containers can be quickly scaled up to handle increased load, making them perfect for dynamic workloads. Virtual machines take longer to scale, but provide more consistent performance for resource-intensive applications. Understanding these use cases helps organizations choose the right technology for their specific needs. Modern infrastructure often combines containers and virtual machines to create optimal solutions. Organizations can run containers inside virtual machines, providing additional security while maintaining flexibility. Kubernetes serves as a powerful container orchestration platform, managing deployment, scaling, and operations of application containers. In hybrid cloud deployments, organizations can leverage both private and public cloud resources. This allows for flexible workload distribution and optimal resource utilization across different environments. By combining containers and VMs, organizations can optimize resource usage while maintaining security and isolation. This hybrid approach enables dynamic scaling and efficient resource allocation based on workload demands.